second. Okay, everything seems to work fine. Welcome everyone. It's our first seminar this year, so Happy New Year. I think we can still wish ourselves a Happy New Year throughout January. So welcome to our Warsaw University Astronomical Observatory Tuesday seminar series. And today our guest is Jan Skowron from our observatory, who's going to tell us about the reddening maps of the large and small Magellanic Clouds based on the OGLE-IV Red Clump stars. Jan, please.
Thank you, Łukasz, for invitation. So this is our recent paper about the largest reddening maps of Magellanic Clouds. It has been accepted to APOGEE supplement series. I think they are waiting for 2021 year to publish it. So red clump stars, why we use red clump stars? It's obvious because red clump star phase is a core helium burning phase for stars, and they keep a similar brightness throughout the long time. So they are useful for measuring distances and extinction, and also red clump stars, because they have similar color for a long time, they will hold the color. So we can see that on those two example plots from OGLE, we can see that the red clump consists of a packed ensemble of stars at given color and given magnitude. So what does reddening do to stars? They basically, if there is a dust between observer and the star, we have the stars appear fainter and redder. So this is shown here by the reddening vector in red. And we would see this kind of color magnitude diagram if we had a bunch of stars separated by a thin cloud of dust. So let's say half of stars are not reddened, the other half is reddened. So we have this two modal distribution. And if the stars are actually embedded in the dust cloud, this is shown on the right plot. The stars are embedded within the dust, so they are reddened differently. This is called differential reddening. Basically, if the stars are in front or behind the dust cloud, they are still compacted on the color magnitude diagram. If they are embedded within the dust, they are spread in color and magnitude. This is also shown here on the CMD of in two different directions towards large Magellanic Cloud with histograms. The narrow histogram in color A, and the B panel is a white histogram in color, and also in magnitude it's narrow and white. So why do we want to study dust? This is obviously there are many interesting objects in the large and small Magellanic Clouds. So we want to have some idea about amount of dust between us and these objects, these individual objects. Also in the Magellanic Clouds, we have distance indicators. We create period luminosity relations for Cepheids and other stars. So it's useful to have a dust contents of LMC and SMC, large and small Magellanic Cloud, and the dust between us and those galaxies. We also would like to use dust to calibrate the tip of the red giant branch. Basically the magnitude of this tip to be able to construct the distance ladder to further galaxies in the universe. And also dust can tell us something about the structure of the galaxy itself. So this is the motivation for the study. Here I show you an optical image of large and small Magellanic Clouds. These are satellite galaxies. People think about them as a small galaxies, but actually they are very, very large galaxies indeed. And we have dozens of smaller satellite galaxies. So LMC, typical knowledge was that the LMC is an irregular galaxy orbiting the Milky Way, and this is a typical image you would see in the books of LMC. But actually LMC is a disk galaxy with a bar. So I constructed the same image is on the right and on the left, but on the right is in more contrast, and you can see loads of stars around the bar of the LMC, and this star create disk which is flat, and it's elliptical, not circular, but a little bit elliptical. And it has sharp truncation at the edge, and the diameter, the largest diameter, the major axis of this disk is 14 kiloparsecs. So if you think about 8 kiloparsec distance between the sun and the galaxy center, the LMC is much, much larger than that. So the reason it is a little bit elongated, this disk is elliptical, is only because the circular disk that was there before was modified by the interaction with the probably with the SMC earlier in the evolution. But still the structure still is very flat and disk-like with a distinct bar. So this is the same image with higher contrast. The SMC in turn is mangled is basically the shape is much more irregular, but it's not small by all means. It's just elongated along the line of sight. That's why we see this dense core in the center. The largest and the best to date reddening maps of Magellanic Clouds were done based on OGLE-III data and our photometric maps. You can see the OGLE-III coverage. It basically covered the whole SMC and a portion of LMC, but only fraction of its disk and not all of the core. These are some previous studies. Hashke et al. Was based on OGLE-III. There was a year ago, there was a paper by Choi et al. Based on SMASH survey, but also didn't capture the whole LMC. And Gursky et al. Recalibrated basically the OGLE-III data and the coverage is the same as previously. This is a Gursky et al. Study. You can see this is LMC and SMC on the left and on the right. So in LMC, you can still see lots of stars and interesting part of the LMC outside of the covered extinction map. by Gursky. In scale, it looks like this. So we can do better. And OGLE-IV is the way to go. The OGLE-IV extended its camera, thus extending its spatial coverage of both galaxies. And basically now we monitor all the disk of the LMC, and we also monitor halo. We discover RR Lyra stars up to the edges of our coverage. So these are really big galaxies indeed. But this is the best data set to be doing the work on the dust. And actually, when you want to use the red clump for this measurement, these white ellipses are the edges. You can basically do this because the number of red clump stars is dropping really fast at these distances, and outside of these ellipses you do not have good statistical measurement of the color. So this is the best coverage of the dust map we can get. So now I will focus on the most important task at hand, is the measuring the color of the red clump itself. So you can construct a color magnitude diagram or the histogram of color of red clump stars. And these are examples of two such histograms from previous studies. And those previous studies, Gursky et al., Haschke et al., and others as well, used some simple, typically Gaussian fits to find the color of the red clump. So you can see they both used Gaussian fit plus parabola. They claimed that parabola is actually somehow getting rid of contamination from red giant stars, but actually what parabola is doing in the most lines of sights is basically getting rid of the galactic foreground stars that are sprinkled across the field and are just fitted out with this basically constant term. And the Gaussian covers basically the Magellanic Cloud stars. This seems legit, seems okay, this procedure, and these are the plots from the papers, but actually when you look at the real data, it does, and more typical and not the best lines of sight, you quickly realize that this is not actually a good way of measuring the red clump color. And the first realization comes in the shape of red giant branch, which is actually quite significant in both of those galaxies. And typically, in typical line of sight, when you create color magnitude diagram of LMC, you would see a Gaussian-like profile, but actually about 20 or 25% of stars in this region are actually red giant branch stars and not red clump stars. And they are offset in color from the red clump stars. And this is even more pronounced in SMC, where the offset is larger and the locus of red clump is narrower in SMC. So immediately it's obvious that the Gaussian fit will not recover the true red clump color. But this is the state of the art till now. So what we do to counteract this problem? First, we want to cut the red clump sample in the magnitude as well as we can. And in order to do this properly, we will not use I-band magnitude because the differential reddening actually makes the red clump size in spread of the red clump in I-band wide. We use the Wesenheit index, which is along the direction of the reddening. So what you see on the right plot histogram is the brightness, which is the histogram, which is along these slanted lines following the reddening vector. So in this Wesenheit magnitude, the width of the red clump sample in magnitude is actually much narrower and much more consistent across different lines of sights, even when affected by differential reddening. Next, we fit two-component function, which is an exponent which takes care of the falling red giant branch stars and a Gaussian-like profile to capture the red clump sample. And we assign the probability to each star based on this fit. And this is the green histogram is our red clump sample that we will measure the color of. Here, this plot shows our algorithm for measuring the color of the red clump. The CMD is at bottom panel. The white band shows the direction of the reddening vector, and the upper panel is the histogram in color. And from the previous fits for the luminosity function, we can actually calculate the probability of red clump stars falling inside our red giant stars falling inside our red clump sample. So we integrate this contamination, and then we will fit the histogram of colors using a red model, which models red clump, and green model, which models red giant branch stars that are contaminating our sample. And the relation between the area of those two fits are bounded by the previous fit to the luminosity function. And you can see immediately that if we will, so the red plus green Gaussians give this dotted black line, which recovers the shape pretty well, and ignoring the red giant branch will shift the measured color by a couple of couple hundredths of a magnitude. The next example is for the SMC, where the influence of the red giant branch is even much more pronounced because the distance is larger and the spread in color is smaller. When we compared our color measurements with the measurements of previous studies, we immediately saw that we actually have disagreements. And we looked into this, and we noticed that these disagreements are of the expected nature. For example, Gursky et al. Typically overestimated color because of the inclusion of red giant branch stars. And in Choi et al., they actually used some manual cuts, manual boxes to recover the red clump sample, and they failed in two distinct ways. First, if they really tried, if the red clump was very narrow in color and the red giant branch was narrow in color, they tried to cut their sample in between by, this is the red histogram in the panel A, and in the process, they cutted away some portion of the red clump sample. In these regions, we saw that they underestimate the color, because basically the color of the sample that is cut will be too, measured the color will be too small compared to the reality. And in high extinction regions, they actually were typically cutting their sample, not constraining their sample to the higher colors, but constraining to the bluer colors, cutting this leading portion. And additionally, they included the whole red giant branch as well. So the color was overestimated. This expected behavior gave us confidence that our algorithm is working better than the previous models. And actually, we generalized our algorithm to cover the lines of sight with differential reddening by introducing this 2 sigma Gaussian. This is a Gaussian profile. Let's look at the red curve first, for example. It's a Gaussian profile that has different sigma to the left and different sigma to the right. The equation for it is written below. And actually, for majority of lines of sight, it's behaving quite nicely. What this is simulating is that if there is the portion of if there is a portion of stars that are embedded inside the dust, and there is portion of stars in front of the dust, then this model makes sense, because the first sigma is the intrinsic scatter plus scatter from the foreground dust, and the later sigma is the scatter of the dust inside our galaxy. And this actually works quite well when you look at the LMC disk, when you expect to have some dust in the disk and you expect to have stars before, in front and behind this plane of dust. And this model works as well for weird scenarios, like on the right panel, when the left sigma is larger than the right hand side sigma, and also for extremely complicated lines of sight. This model is stable. It will not give the best answer, because there is no best answer for these kinds of scenarios, like two-modal distribution. But compared to the differential size of the differential reddening, the answer is as good as any other answer will be for this line of sight. So we report these feeds as well. So now I can present the results of this study. First, this is the plot of red clump stars density on the sky. You can see that the small Magellanic Cloud is the density is falling more regularly, more uniformly in distance from the galactic center. But for large Magellanic Cloud, first is the sharp drop of density when we go off from the bar, galactic bar, and then the density is falling exponentially, as we would expect from the disk. And at this dotted line, there is a very sharp drop of density of stars per square degree. So this is a cutoff of the galactic disk, basically. The next map we are getting, the main map we wanted, is the measurement of the red clump color, V-I. And this is actually quite interesting because you can see all this noise outside of the red of the white circles, and this is actually when the number of red clump stars from the LMC or SMC is much smaller than the number of stars from the foreground Milky Way, and the algorithm is misled. So we do a visual inspection of those lines of sight, and we decided to cut our map at this white ellipse, not to include anything outside, just because we don't feel it's reliable. And it's seen in small Magellanic Cloud map as well, when we look at the color inside the white ellipse, and outside there is a sharp drop in color. So this is also because of the contamination from the foreground stars, dominating contamination. What you can see as well is that there is two halves of the LMC. One half is has much less dust in front of the stars, and the other half has much more dust in front of the stars, and loads of dust near the center of the LMC. Not in the bar per se, but in the star forming, close to the star forming region of Tarantula, there is loads of very dense dust clouds. So in order to make sense of these two halves of the galactic disk, of the LMC disk, we can look at the spread, the width of the histograms, basically the spread in the red clump color. And this is the map of the sigma of the color distribution, and the sigma is elevated within this black circle, and outside of this black circle, this sigmas the spread is very, very uniform, and there is no difference between this half of the LMC, the south half, and the north half of the LMC. This indicates, and there is huge sigma outside the circle, so this indicates the big contamination from the background, from the foreground stars. So, and the lack of the, so the sigma in front, in the center of LMC, is understood as a differential reddening. Basically, the stars are embedded in the dust clouds, and they produce a large range of colors. But the lack of the spread in the disk, southern disk of the LMC, suggests that the whole dust, all dust that created this reddening is actually in front of the stars in the galactic disk. So the whole reddening happens in the way toward the LMC, and inside the LMC there is no significant reddening in this region. So this is foreground dust. and in the galactic center we have the dust from the LMC itself. This is a plot of the reddening based on Schlegel paper. The Schlegel et al. Took observation of COBE and IRAS satellites to measure the emission of the dust. And from the emission, they calibrated the mass and the reddening that would be caused by the dust that is emitting the infrared light they see. So what we can see is that in the galactic disk, in the LMC disk, we have these clumps. We have these clumps of dust that are obscuring the view of the LMC, and we know that these are the foreground dust clouds. But funny thing, interesting thing is happening in the center of galaxies. And it is known from the very long time that the SFD, the Schlegel maps, are not reliable in the center of LMC and SMC. People knew this because they give crazy values, but now we can see immediately by the comparison with our measured color that we do not see this kind of features, but they do. So the reason for this is basically this emission they were using for their calibration. You can see the emission from the Milky Way gas all over the image, but the emission from SMC and LMC is very different. The gas is hotter, it has very different properties, and the calibration they were using to create their maps completely breaks. There's different gas to dust ratios, there are different metallicity, the calibration breaks. So the Schlegel maps are completely unreliable in these regions. However, because we have this huge coverage of the LMC and SMC outside of this problematic region, we can compare the reddening the Schlegel saw with the color we see, and we can calibrate the intrinsic color of the red clump based on this. So this is the difference between our color that we measured and the reddening from the Schlegel map. And immediately what can be seen is that in the disk of the LMC, not in the center, in the disk of the LMC and outside of the SMC core, though both of those maps agree, and the agreement is very uniform. There is no structure, and actually our maps agree quite well in this region. So that's why we decided to use all of those regions to calibrate what is the true intrinsic color of our red clump sample, and use this intrinsic color to calculate the reddening inside of the black ellipses where the reddening is not well known. This is exactly this exercise I was talking about. We have panels C, D, E, and F are the 4 quadrants of LMC, and the blue northeast, northwest, and so on. And the blue, for each quadrant, we have three plots, and the blue plot shows the reddening from Schlegel maps. The red dots show color measurement from OGLE, and the cyan dots show the difference of those, which indicate the intrinsic color of red clump in the LMC. And what you can immediately see is that this intrinsic color is very much flat, with a slight maybe hint of a gradient, but also consistent with being flat. So it's nearly, so the intrinsic color of the red clump population in the LMC is nearly constant across the disk, and here we remove all points inside the black circle and removed all points outside of the white ellipse, which are not reliable. For the SMC, the situation is very similar, except one thing, that we see a bifurcation in the measured color. We have two distinct here groups of points, and this corresponds basically to the southern and northern part as well. And the southern part is just a galactic foreground dust in front of SMC, and here we lack this foreground cloud. This bifurcation shows in our maps and in Schlegel, and after subtracting, the intrinsic color is consistent with no gradient or very small gradient of intrinsic color of the red clump. So having the intrinsic color, we can basically calculate the reddening. We were thinking about the gradient we see, and many people tried to argue that the gradient is important, the metallicity gradient, which creates the gradient in intrinsic color of the red clump. So we decided to check this. This is the calibration where we took loads of clusters with different metallicities on x-axis and with a measured V minus I color of the red clump in them, and we created this red the red model, how the intrinsic color would behave with the changes of metallicity based on clusters. This is similar to theoretical values with this violet line is in agreement, but we use this empirical relation. And then we took the metallicity of red giant stars measured from APOGEE in LMC and SMC, and plotted the metallicity across the distance from the center of both galaxies. And here is the center of LMC and the edge of LMC, and you can see that the metallicity, which is on y-axis, of all of those magenta points, each magenta point is a measured red giant branch star and its metallicity. You can see immediately that there is in fact a small gradient of metallicities across the disk of the LMC, and the same can be told about the SMC, where we see a gradient, but the gradient behaves a little bit differently. The core of the SMC is much more metal rich than the outside of the SMC. So we introduced the two gradients, basically gradient for the center and gradient for the rest of the SMC. And then we can basically plot those gradients here, and the dashed lines are those gradients, and we can see that the data is absolutely consistent with the gradient slight gradient seen in the data, with a gradient consistent with the metallicity change in the LMC. And the same goes with SMC. We can see that the black line is the gradient of the outskirts of SMC, and orange line is how the intrinsic color of the red clump would change if we introduce this sharper gradient in the center of SMC. This was our take, but the previous studies had their own takes. For example, Choi et al. Postulated that the color, intrinsic color of the red clump varies in the center of the LMC. It's small, then it's higher, and the edge is very low. But we checked this with our data, and it's false. Basically, they made a mistake. They calibrated the intrinsic color on this chosen region. This is the LMC, part of the disk of the LMC and the LMC bar, and they chose some regions and calibrated the color, intrinsic color on those regions. But and we repeated their exercise. We took our data, their regions, and we plotted intrinsic color we would see. And yes, of course, it's low in the center, then higher than low at the back. But when we actually remove all the data we do not agree with, we think are contaminated outside of this white ellipse. And when we remove the data from the inside affected by the wrong Schlegel map, then the upper panel is our measurement, and we can see that all those artifacts from Choi et al. Paper disappear, and we have flat gradient consistent with the metallicity gradient. And when we put LMC, our measurement of the LMC, the center of the LMC and the edges of the LMC, and center of the SMC and edges of the SMC, they are very much consistent with all the red clump stars in clusters we see. So the final result is this reddening map. The reddening map is much more accurate than you can see on this picture, because we studied different lines of sight. These are densities of those lines of sight. The red ones are, there is a measurement every 1.7 arc minute, and the size of the box we measure the red clumps, we measure the statistic is 3.4 arc minute, and when the density of stars is dropping, then we make the box sizes larger. But you can really go to very, very fine resolution with this map. You can also see differential reddening. And what's very nice, and I like this plot a lot, is that the center of the LMC, you can immediately see this disk, this inner dust disk of the LMC, which is creating the most of the differential reddening within LMC, and was seen in this beautifully on this infrared emission from the infrared satellites. So the LMC has its inner outer disk and inner dusk disk, which is flat and rich in gas and rich in dust, and it's slightly offset from the bar and slightly offset from the center of the galactic disk, LMC disk, and all of these was probably due to interaction with SMC, and also the gas disk is sharply truncated. This also suggests that the previous interaction, there was dust probably outside of this region as well, but it was truncated by some dynamical process. We provide the full website with the interactive interface to calculate the reddening toward your favorite line of sight. This is the URL for this website, and the website allows you to put galactic or equatorial coordinate, allows you to upload the whole file with coordinates of different various formats, and will give you all of those measured values like reddening from Schlegel, reddening from us, color measurement, intrinsic color measurement or measures of differential reddening. Also, we can use an interactive clickable map. If you click anywhere on this image, the values, reddening values will be reported to you for every line of sight you click. You can also look at different data like only Schlegel maps or only differential reddening or only infrared emission. And also this data is available in the FITS format. When I combine this huge FITS file with 7 extension, and each you can click, you can zoom, you can use some program to extract values for reddening. The sigma 1 and sigma 2 is the left sigma and right sigma. Median color, intrinsic color of the red clump, and also size of the box it was measured with. So as for now, I think this is all I have time to report to you, but there are some more interesting developments we'll probably share with you during the next Tuesday seminar in a couple of months, I hope. Thank you.
Okay, thank you, Jan. I'll do the clapping on behalf of everyone. I noticed that you had 45 slides out of 50, so and I was eagerly waiting to see the remaining 5, but you left the suspense, saying that okay, there is more you have, but you don't want to share with us yet. But anyway, thank you for this. So questions, please. If you want to ask a question, please raise your blue hand in the participants menu, and I will then ask you to speak and show your face, possibly. I've seen Marek Górski here among the participants. What is his view on your results? Marek.
Hi, hello, everybody. It's nice to see, actually, a lot of people from observatory. Well, I would like to say that this is very impressive paper, and the results are, again, very, very interesting. We talked already a few times with Dorota about the disagreements actually that appear between your paper and our results. And this is also something that seems to raise a lot of questions, especially concerning reddening law, also concerning different kind of populations, the questions about how well actually we understand what is the intrinsic color of the red clump and how it depends on the metallicity and the age. However, one thing I would like to say is that I'm really very impressed with the kind of the filter, with kind of a statistical analysis that you used to calculate the color of the red clump. And definitely it is a much better approach, especially when we have this very high values of the intrinsic reddening in both clouds. So this would be my comment. And again, I think that this difference of the values that we obtained from different reddening tracers and the approach that you have in the paper actually is a kind of the open question, and the further research will be definitely very interesting also.
Yes, so Marek alluded to one very interesting point we noticed. Basically, there is a disagreement between the stars that had reddening measured from the spectroscopy in LMC and SMC. You can see the dots which cover the large parts of the bar and center of the LMC. And we actually noticed that in our paper that the disagreement between the values from the spectroscopic calibration and the disagreements between the values obtained by us actually correlate with the density of stars in the bar. So if you go to low densities, our results agree. But if you go to high densities of stars within the the LMC bar, then our results disagree, and we don't know yet if this is problem with the calibration of the spectroscopic method, or if it's a problem with our understanding of metallicity, age, or population, basically, of stars within very, very narrow bar. So we stand by the result outside of the very, very narrow bar, but this comparison shows that there might be some problems in this very, very dense region inside of the LMC. So this is the kind of things you learn when a couple of people do the same thing and then see some new science emerges from it.
Okay, thank you for those comments. Are there any questions, other questions? I have a quick one. I'm always impressed by all the interfaces you make, like the interactive plots and so on. However, my question is whether I can query this data from a script, for example. Is there an API which I just type in my program and it gives me the value for given coordinates? Is it possible?
Yes, there is an API working inside the observatory. Let me know. I can give you a link. And for all other listeners, if you have really, really huge list of coordinates, you can just send me. I will use this API in the background and send you the result if the web interface will not give you results fast enough. But I'm pretty sure for reasonable number of objects, the web interface will work pretty speedy.
Okay, great. Thank you. I don't see any questions, neither here on Zoom nor the YouTube. So I will thank you, Jan, for this talk. Do the clapping again on behalf of everyone, I think. And thank you all for joining, and see you next